Welcome to this last module of this particular class, or you can say lecture, and this is on micro machining, right. So, along with micro machining, we are also looking at CVD in particular, which is your chemical vapor deposition. Now, we have taken few examples of sensors, how you can fabricate sensors using bulk micro machining or bulk plus surface micro machining, or if it is a actuator that can actuate the mirror, or it can be a cantilever, how can we use this bulk and surface micro machining, right. We also see we have also seen the advantages and disadvantages of dry and wet etching. Now, in the thin film deposition, when you want to grow or deposit a thin film, there are two techniques. We have already discussed PVD, which is plasma, which is a physical vapor deposition, and in this PVD there is again subdivision. One is evaporation and another one is sputtering. So, when you talk about evaporation, you have thermal evaporation and you have E-beam evaporation, and when you talk about sputtering, sputtering is a mechanical way of dislodging the atoms from the target and deposit the film on the substrate, right. So, when you talk about chemical vapor deposition, the chemical vapor deposition have inherently better or few advantages over PVD, and those advantages are it can have it will have a better step coverage, the quality of the film is better, and it is generally used to deposit silicon and insulators. So, depositing growing a silicon or SiO2 or Si3 and 4 silicon dioxide or silicon nitride with CVD is better. Also, the purity of the film is better in case of chemical vapor deposition. So, having said that, let us see what kind of chemical vapor deposition are there and what exactly chemical vapor deposition means. If you recall, we have seen this kind of arrangement sometime when we were discussing about wet etching, wet oxidation and dry oxidation, right, wet oxidation and dry oxidation. So, chemical gas sources are thermally, optically or electrically plasma activated to react with a surface to deposit a layer, and byproducts are pumped out from the chamber. So, we were introducing O2, right, at very high temperature about 1100 degree centigrade, right, and the byproduct was out of this particular furnace. Similarly, 1100. Similarly, in case of vapor, right, H2O, right, the vapor of the water vapor were carried out carried inside this particular furnace, and it reacts with the silicon to form SiO2 plus 2H2O, right, which was the byproduct, and that would come out of the chamber, right, of the furnace. So, point is that the byproduct will come out after reaction, and that is what is written. Dry products are pumped out from the chamber. In a simplified model, as a gas flows over the substrate, film growth is determined by absorption, adsorption and reaction rates, correct. So, you can see here the gas is flowing, main gas flow region, gas phase interaction, right, transport to the surface, there is a surface diffusion and a readsorption, right. Same way there is a desorption, and this is how the film starts growing. So, when it is adsorption or if it is a desorption, then desorption occurs because of the so first of nucleation, island and step growth occurs, which you can see here is a nucleation, and then slowly a island will form following by the step growth, and of course, there is a desorption which are the not which are the byproducts, and that can be pumped out of the chamber. So, the point is that using CVD we can deposit several films, in particular insulator and silicon. So, when we say several, that means just limited to insulators and silicon, right. Now, in reality the deposition rate is affected by distance from the gas inlet, right. These are the factors, specifics of the reaction, and radial variance. How to improve the uniformity then, right? So, you can tilt the substrate into flow, right. You can see here we have tilted the substrate, instead of placing substrate like this, we have substrate placed in this particular position, right. So, we have tilted the substrate, increased temperature along the substrate and single wafer processing, right. These are tricks to improve the uniformity of the film. So, when you talk about CVD, how many types of CVD are available? So, we have 4 basic type of CVD that we will be talking about. First one is atmospheric pressure CVD, it is also called APCVD. The advantages of this CVD are high deposition rate, simple and high throughput. Disadvantages are poor uniformity and purity is less than LPCVD, right. So, what is used for APCVD? APCVD is used for thick oxide deposition, right. Now, when you talk about LPCVD, LPCVD can be used at 0.2 to 20 torr. Advantage is excellent uniformity, purity. Disadvantage is lower but reasonable deposition rate than APCVD, right. Is used for polysilicon deposition, dielectric layer deposition and doped dielectric deposition. Now, when you talk about metal organic CVD, which is also called MOCVD, its advantages are it is highly flexible, can deposit semiconductors, metals and dielectric, right. In PECVD or LPCVD or APCVD, generally oxides are used or oxides are deposited or polysilicon is deposited, but in case of MOCVD we can also deposit semiconductors and metals. The disadvantage is being highly toxic and extremely expensive, and environmental disposal costs are also very high. However, MOCVD is used for low cost optical 3-4 technology, right, some metallization processes which includes tungsten and copper. When you talk about plasma enhanced CVD, which is your PECVD, plasmas are used to force reaction that would not be possible at low temperature, right. Plasmas are used to force reactions that would not be possible at low temperature. Advantages being uses low temperatures necessary for back end processing. Disadvantages being plasma damage typically results and used for dielectric coatings, right. So, these are the advantages, disadvantages, and generally it is used for dielectric coatings. What is PECVD? Also we can grow, the advantages are low temperatures, you see. So, we can deposit silicon dioxide or silicon nitride, right, at relatively low temperature like from 100 degree centigrade to 400 degree centigrade is a relatively low temperature that plasma enhanced CVD chemical vapor deposition uses, and that is why it is used in MEMS application, MEMS based sensor fabrication, which we have just seen, where we can grow silicon dioxide with PECVD. So, when you talk about LPCVD, LPCVD typically uses silicon containing compounds, typically 100% silane, SiH4 or 20-30% silane or 80-70 inert gas, and which are reacted with wafer at 0.2 to 1 torr and about 575 to 650 degrees centigrade, right. LPCVD is used for polysilicon for gates contacts. Polysilicon can be doped using diborane or arsine, right, B2H6, ASH3 or phosphine, which is PH3. Doped polysilicon makes good short interconnect lines, right, we know it. Thick oxide used for oscillation between metal interconnects, right, these are also used with LPCVD, right. Doped oxide uses is useful for global planarization, as well as nitrides and other dielectrics for isolation of capacitors like high K dielectric material for large capacitance, right. So, LPCVD is useful as well, since silicon nitride is used for encapsulation, that is sealing of the circuit to prevent contamination from moisture, plastic used in packaging or air. So, LPCVD is used in this particular processes. However, LPCVD consumes less amount of expensive gases as compared to APCVD. So, then how APCVD works, right? Another question to us would be how APCVD works. So, we will see that APCVD later on. Let us first see MOCVD. So, MOCVD, many materials that we wish to deposit have low vapor pressure and thus are difficult to transport via gases, right. So, what is the solution? The solution is to use MOCVD. So, if you look at the screen, one solution to chemically attach the metal, right, that is gallium, aluminum, copper, etc., to an organic compound that has very high vapor pressure. Organic compounds often have very high vapor pressure, for example, alcohol has a strong odor, right. The organic material bond is very weak and can be broken via thermal means on wafer. Depositing the metal with very high pressure, organic being pumped away, right. So, care must be taken to ensure little of the organic byproducts are incorporated and carbon contamination and unintentional are unintentional. Hydrogen incorporations are sometimes a problem. So, this is about MOCVD. When we talk about PECVD, so as you can see a system here, there is a heated plate, there is a inert gas and process gas that we can insert in the system. There is a RF power due to which there will be creation of plasma, and when the gases reacts with each other, it will get deposited, the film will get deposited on the wafer. So, what is exactly why we have to use PECVD? PECVD. So, let us take an example here, which is shown right over here. Now, if you have an oxidized silicon wafer with aluminum metal coated on the wafer or deposited on the wafer, and on this if I want to grow silicon dioxide, you want to deposit silicon dioxide. Now, all the other methods they have extremely high temperature, but in case of PECVD this can be grown or deposited at a lower temperature, about 100 to 400 degrees centigrade. There is an advantage of PECVD. So, suppose after metal lines like aluminum was deposited, how would you deposit a conformal dielectric SiO2 or Si3N4 to isolate next metal layer, right. So, if I want to have another metal layer, I have to have silicon dioxide in between these two metal, right. This is another metal, this is one metal, right. So, this one would be my insulating material, correct. The silicon dioxide would be an insulator. We have just taken example of gas sensor, right, where we were depositing a silicon dioxide between a heater and interdigitated electrodes. So, solutions includes PECVD deposition of dielectric. When fast diffusion metal like copper are used, this low temperature deposition becomes more important. So, what are the advantages of PECVD? The advantages of PECVD are: first, it is a low temperature process, right. Second, provides reasonable deposition rates. Third advantage being good film quality, the quality of the film is excellent. Next advantage would be conformal. Finally, we have lower chance of cracking of films, right. These are the advantages of PECVD. While when you talk about disadvantages of PECVD, it mainly may leave unwanted byproduct on films, costlier, while the stoichiometry is not guaranteed. For example, SiX and Y instead of Si3 and 4. So, this we do not know exactly it is Si3 and 4, we cannot really guarantee the stoichiometry, right. These are the disadvantages or limitations of PECVD. So, why not CVD is commonly used in lab? When you see except few bigger fab labs, generally CVDs are not commonly used, and the reason is because of the safety factor. Many gases that we used in CVD, are toxic, that is hazardous to humans. It is corrosive, that it causes corrosion to stainless steel and other metals, and it is flammable, that is burns when exposed to an ignition source and an oxygen source. It is also explosive and or pyrophoric, that is spontaneously burn or explode in air, right. It spontaneously burns or explodes in air, moisture or when exposed to oxygen. So, these are the reasons why you will not find CVD very common in laboratory. Now, if you if you see sorry if you see gas is hazardous effect, flammable limits and exposure limit, then you will see that ammonia is a toxic and corrosive gas, flammable limits about 16 to 25%, while exposure limit is just 25 ppm. Same way you talk about silane 0.5 ppm, arsine 0.05, phosphine 0.3, hydrogen chloride 5, diborane 0.01, dichlorosilane 5. So, the exposure limit is extremely small, right. You need to be extremely careful when you are using CVD. Again you see the flammable limits also, that it is pyrophoric when it is silane and phosphine, while hydrogen is between 4 and 74, diborane 198, dichlorosilane about 4 to 99, and most of the gases are either toxic or corrosive or flammable, right. For example, if the corrosiveness comes, then ammonia and hydrogen chloride are corrosive. If it is toxicity, then all the gases like ammonia, silane, arsine, phosphine, nitrogen diborane as well as dichlorosilane, these all are toxic. And when we talk about flammable gases, then silane, phosphine and diborane and dichlorosilane, these are toxic gases. So these are flammable gases, not toxic, they are flammable gases, right. So, in short, what we understand is CVD can be used for depositing insulator or an oxide layer. Insulator is oxide or silicon nitride layer. It can also be used to deposit silicon, and it has advantages over PVD in terms of its film quality, in terms of better step coverage, and there are several kinds of CVD, and what is interesting to us is one that we used for growing wet oxidation, for growing oxide at high temperature. But another one that is also interesting to us for this particular MEMS based sensor is PECVD. Why PECVD? Because PECVD can grow insulating material at a lower temperature. A lot of applications we require insulator between two metals, and we can take help of PECVD, right. So, this would be the end of this particular lecture, which consisted of several modules, and I wish and I will urge you guys to that you guys will read again. First is I wish that you guys read again, second is I will urge you to read again, because it is very important to understand how to use micro machining, and then it is also important to understand what kind of devices you can fabricate using micro machining, also what kind of chemical vapor deposition techniques are used. And understanding this is very important, because when we actually go to a fab lab and see how the things are executed, you will understand, because you have already covered this thing in theory, right. When we talk about photoresist, positive photoresist, negative photoresist, lithography, we talk about BHF, or we talk about silicon etching, right. We talk about the deposition of gold or chrome or any other metal. So, in all these things we are talking about photoresist developer, right. So, when we know it on theory, when we know the process flow, then it will be easier for us to understand when in one of the course that I may be taking in following semester, where where the students will be shown how the device is fabricated in a fab lab environment. So, all these things would be useful when you want to understand from fab lab perspective, right. So, till then you guys go through this lecture, have fun, right, enjoy your life. It's a not so difficult things, but it is important to thoroughly understand this subject, and I am sure you will do well and use this knowledge to create novel devices. Bye.